Excuse me, ma'am. Nag-start na ka, ma'am? Wala lagi audio.
Yeah, nag-start na ka, sorry. Okay, so I was talking about, last time we were talking about the radical reactions, and one of the reactions that is present that will be applicable to biological system is the oxidation process. No, so actually today we will proceed with chapter 11, but I would just like to point out that there is also a process where the auto-oxidation process in the biological system can be minimized rather, in the presence of some antioxidants that we call, and usually those antioxidants are the phenols and ethers. So just this is just a side note. Before we start chapter 11. Okay, so how does the auto-oxidation occurs? Now, in auto-oxidation, usually you have your fatty acids with a hydrocarbon chain, and in the allylic position, you have your hydrogen there that can be cleaved in the presence of oxygen and light or heat. And what happens is that in the presence of heat and light, this actually can be cleaved here, this position here, and you actually get a stable allylic radical. And once you have that, can add to this oxygen to form this one, and by homolytic bond formation with the O2 here will have O double bond O, right? So what will happen is that the O dot, once the O double bond O, okay, the C dot, because this one will cleave the presence of light or heat, you'll get a radical. Once you get the radical, you actually get the C dot, the electron, one electron here that would come from here, and then another electron from oxygen. You would form a bond here. Now this is a homolytic bond formation from one electron of carbon brought by the homolytic bond cleavage from here, and then you will have here. So where would the other one electron comes from? This one electron would come from the double bond, double bond becomes oxygen to form in here now. And then the one dot electron hydrogen here will also react with the hydrogen that will be clipped from here. Anyway, so this is just, and I'm just showing you that this is an example of the auto-oxidation process that would occur sa mga fatty acids and hydrocarbon chains, and mostly biological system or kanang mga food samples, no, with have biological origins, organic origins. Okay, and what is being produced is the hydroperoxide. But in the presence, yes, this is what I'm saying. Atoms or molecules with an anchored electron, you have this, the radical. We have already discussed that one. So in the auto-oxidation process, this is, I have been saying, others here showing the mechanism. In the presence of heat and light, you actually produce a radical here. See that this is an allylic radical. If you notice, this carbon here is adjacent to this double bond carbon. So this radical here, see that is actually an allylic radical. Okay, and what happens is that after you form your radical, there's a chain propagation step. You actually get a bond formation with the oxygen, which is a diradical. In the presence of heat and light, the O, usually, if you remember the love structure of your oxygen, it's O double bond O. Okay, the O double bond O, but in the presence of light, we also have the pi bond from the O double bond O. Now will be cleaved, and you also have a diradical of the oxygen. Okay, and so these atoms, there's one electron from the carbon that here, and one electron from the oxygen will form a bond. Get this one. Here, your radical now will be on the oxygen. You have your hydroperoxide radical, and what happens next is, of course, in the presence of the fatty acid, this one will be cleaved. You will actually use this radical here to form a bond with a one electron from hydrogen. And so the process will be repeated. Okay, and what you will get in the bond formation of this is the allylic radical originally from your fatty acids, like here. Okay, so, and then you just repeat on the cycle, you repeat in the cycle. That is the auto-oxidation process. So in the hydroperoxides themselves are unstable and under biological conditions. Kasi itong mga hydroperoxides, kanyang mga inani. Okay, these are actually unstable and they always they're unstable and under biological conditions, they degrade to short chain aldehydes and carboxylic acids with unpleasant rancid smells, and that is the usual auto-oxidation process. So when you've noticed, you will notice in food samples or even your body, no, and you smell some kind of rancid odor, particularly sa mga fatty foods, no, even sa mga fatty food samples, no, easily can smell already a rancid smell, and this is because of the formation of hydroperoxides or radicals because of the auto-oxidation process that's going on. And similar formation of hydroperoxides in low-density lipoproteins deposited on walls of arteries leads to cardiovascular disease in humans. In addition, many effects of aging are thought to result from the formation and subsequent degradation of hydroperoxide. So in other words, and when you see the reaction earlier, when you produce the hydroperoxide, can actually be favored, no, once we are exposed to heat and light, especially if we have oily skin. So if you want to prevent the auto-oxidation process or minimize at least, we have to always prevent our skin, especially pag oily atong skin, to the exposure sa sun and heat. Okay, because it will always produce hydroperoxides in the process, especially no kanang mga, of course there's a lot of oxygen here on Earth. So fortunately, nature has developed a series of defenses against the formation of this other destructive hydroperoxide. We want to slow down and prevent this formation of hydroperoxides or the formation of auto-oxidation process. At least we want to slow it down. And the usual compound that we use are the vitamin E. They are what we call as nature's scavengers. So what is a vitamin E? You can see the vitamin E. It's like you have here a phenolic group. What is a phenol? Once we go to the chapter aromatic compounds, benzenes, and aromatic compounds, you'll see a ring here of benzene and with an OH that's phenol. You can also see here like an ether structure here. So this is your vitamin E you have here. And this is usually added, no, or especially sa mga cosmetics, no, personal care products to at least slow down the formation of hydroperoxide, which is very destructive to the skin. And then also for food products, they usually add antioxidants, usually the BHT or the BHA, the butylated hydroxytoluene like this one, or the butylated hydroxyanisole like this one. So I'm just pointing this out because Solomon's was showing the auto-oxidation process, the mechanism isn't clearly shown. Okay, so unfortunately, vitamin E, usually before now, they have to add vitamin E in food processed products. So unfortunately, vitamin E is removed the processing of many foods and food products. So to make up for this loss, phenols such as BHT and BHA, earlier, what's common with this is they have a ring here with an OH. It's like a phenol, like an alcohol with an OH. These are not alcohols, but those are phenols, and the properties of alcohols and phenols are quite. For the next chapter, we'll be talking about alcohols. Okay, so what is to minimize again, as I mentioned on to minimize on the auto-oxidation formation of hydroperoxides, they usually add vitamin E, but for food and food products, they have already eliminated vitamin E. I think it's because it's more expensive. They would rather use vitamin E for personal care products. Because manufacturers are using vitamin E for mga personal care products and cosmetics. So for foods, they usually use BHT and BHA. They are added to foods to retard spoilage. You don't want, of course, our processed foods. You want our foods to be preserved for a longer period of time. You don't want to have our food rancid. We to already produce rancid smell in a short period of time. So we want to minimize that one. And they usually add BHT and BHA. Likewise, similar compounds are added to other materials such as plastics and rubbers to protect them against auto-oxidation. And you will notice, no, even some plastics and rubbers, once it's being exposed to sun and light, no, there is a certain odor that you can smell, and that is because it also would undergo some kind of auto-oxidation, and they would add another antioxidant to prevent that process. So if you don't have like BHT or BHA, sometimes there are so many sources of phenols from plant sources that would minimize the auto-oxidation. For example, some plants, let me see. I have some here, some example. This one, the thymol, for the thymol leaves, even vanillin you have here. There is a certain smell for vanillin. If you're baking cake, you can see here there's an OH here. Thymol from thymol leaves, kanang mga paminta, right? From thyme, can have this one. And that is the reason why kanang mga, if you put a lot of spices in your food, the spoilage of the food that you prepare actually will take longer as compared to when there is none, because this compounds can also act as an antioxidant that prevents auto-oxidation process that would go. Okay, so for the rest of chapter 10, it's radical reactions, I'd like you to read, and there's some reading portion in chapter 10. I'd like you to read for some other info that you like. So for now, we'll proceed with another chapter, which is alcohols and ethers. It's another chapter and another functional groups, another class of organic compounds that we'll cover. And yes, I have already mentioned vanilla when we are taking some plant materials, like spices, foods. You notice, for example, if you're mahilig with drinking mga tea or mga milkshake, sometimes they would add peppermint, and there's actually can smell certain odors because of the menthol. And you have also vanilla from vanilla beans, vanillin from vanilla beans. If not, you can have a vanilla syrup. If you're into cooking and baking, you can immediately smell the vanillin. And yes, I have already introduced this earlier. It can also act as an antioxidant to prevent fast spoilage of foods that's being prepared. Okay, also have your alcohol here. This one is an ether, and can also get this one from fennel leaves. Now this comes from actually some plant sources, and you'll notice here that there is a similar structure for all of this. Here you have your alcohol, your OH group. Here you have your OH group, but this one is bonded to a ring. You also have here like kind of an ether, but it's bonded to a ring, and so on. But what we'll be discussing today will be focused on alcohols and derivatives of alcohols, which is an ether. So the alcohol carbon atom may also have here the unsaturated, or rather saturated one, OH here. So the alcohol carbon atom may also be a saturated carbon atom adjacent to an alkyl group like this. This one, so your OH can also be adjacent to your OH attached to your carbon at an allylic position. So you always have to be mindful when it's an allylic position, because there might be brought some kind of stability, or even when it is at the benzylic position. Okay, so this is also an alcohol. So the functional group present with alcohol is your OH. Whenever you have an OH, then you consider that to be an alcohol. And when one of the hydrogen is being replaced with another R group, like this one, OR, consider that one to be an ether. So here you have 2-propanol, which is at an allylic position. You see an OH here, you see an OH here. And compounds that have hydroxyl group attached directly to the ring, benzene ring, you have here, as I mentioned, you have your phenols here. So these are examples of phenols. These are some kind of important, it's like an alcohol that's bonded to the ring, and we'll see later that this phenols and the normal alcohol, like this one, bonded to a non-ring, not bonded to a double bond in a ring, no. They actually have separate properties. And we'll see later that we'll focus on this chapter, the 1 degree, 2 degree, and 3 degree alcohol, and that is kind of phenol. And this one, we will tackle this when we reach aromatic compounds. So here also you see an OH here bonded to the ring. It's also a phenol. And you have here the general formula of our phenol. The compounds that have, so for ethers, they differ from alcohols in that oxygen. I have mentioned earlier that the oxygen atom of an ether is bonded to 2 carbon atoms. So you have here an ether. For an alcohol, the O here is bonded to an H. Now for an ether, instead of hydrogen, you see another alkyl group, carbon group attached to it. Okay, so here you have an O, but aside from carbon, it's bonded to another carbon. So oxygen is bonded to carbon and another carbon. Alcohol, you have your O bonded to carbon and another hydrogen. So here's an example of the different ethers. And in the laboratory, activity 1, 2, 3, and 4, but we're able to name our organic compounds, and depending on the functional groups that's present, we will be able to name organic compounds. So for naming alcohols, you always end naming alcohols with an O, right? If you remember. So I think it's easy for you. Just have to refresh your memory here. How do we name this one? A1. Camille. How do you name letter A? This is just, we're not gonna focus on naming here, but it's just a refresher, because we'll be focusing on reactions, properties of alcohols and reactions. We name this one depending on the number of carbon, straight chain carbon atoms that contains your oxygen. So here you have 1, 2, 3, 4, 5. You have 1, 2, 3, 1, 2, 3, 4, 5. So the number of carbon here is 5, and you have an O, H. So we always end with an OH. Or for alcohols, we always end with an O, right? So there's 5 carbon, always end with pentanol, right? 1, 2, 3, 4, 5. So in carbon 1, the carbon with the lowest locant of our OH becomes our carbon 1, okay? Or yeah, so here becomes your substituent. So you have in carbon 2, you have your methyl and methyl, and carbon 2, 3, 4, so you have your methyl and methyl group. So you have 2, 3, 4, 2, and 4 dimethyl pentanol. So the reason that we're just trying to remember on the meanings of alcohols, because sometimes when we are asked for reactions, some structures are not being shown, right? What is being shown is just the name. So for the first case, you have your pentanol, or 1-pentanol is your parent chain, this one. And on carbon 2 and carbon 4 is your substituent. You have 2,4-dimethyl 1-pentanol. So for naming our organic compounds, even as we go to different functional groups or class of organic compounds, we always not forget how we name our organic compounds. We always have to refresh our system for that, and apply the Aopa system of nomenclature, because sometimes when we're asked to the properties and even reactions, we sometimes are given simply with just the Aopa name, and that doesn't include the structure. Okay, so here you have the Aopa system has so apply what we've learned in laboratory. In laboratory in Chem 130, tama. Okay, naman dito ang page. Okay, so here you have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And you have your phenyl group here. So how do you say that one? You can have your substituent on carbon 4. You have your 1, 2, 3, 4. 1, 2, 3, 4, 5. That should have been your pentanol. 1, 2, 3, 4, 5. The longest continuous chain that contains your functional group. So you have your pentane, but you have your OH. So you name this one as pentanol, right? But your all should be indicated, and it is indicated either on carbon 1, 2 or in carbon 1, 2, 3, 4. So it's either 2 or it's carbon 4, so which is the low locant. So you have your 2, 1, 2, 3, 4, 5, 2 pentanol as our parent chain. This becomes our substituent. So what is the name? What is the name, Camille? This one you have nakalimot naman sa name. Anyone who could name this? Letter B. Anyone who could name?
4-phenyl, 2-pentanol.
1, 2, 3, 4. 4-phenyl, 2. Is ito? 4-phenyl. 2. Pentane, delete mo end with ane because you have your all, you have your OH. Once you have your OH, yes, you always end with all, pentanol. From the name itself, you will always have to recognize the class of organic compound that it is, or the functional that the name implies. Not so all, that means there's an OH in the structure. So you don't say pentane, that means there's no OH. So you have 1, 2, 3, 4, 5. Okay, so that's parent chain is pentanol again, but on carbon 2, there is an OH. So your parent chain is 2 pentanol, and on carbon 2, 3, 4, you have your, sa many tawagan ni? C6H5. Tawagan na. Ano si tawag? Sa tayo mag-iingon ko, Ann? Isa man nito ba?
Female, mom.
Isa to dito bag si Koan. Ronel or Niel?
Si
Tumarlas,
Ronaldo.
ma'am.
Si Ronel. Okay, so how do you name
Tumarlas
this?
to, ma'am.
Tumarlas, Ronald. How do you name this? Ronald. 2. 2. You have 4. 4-phenyl dash
Pentanol.
dash
2-pentanol.
2-pentanol. Okay. Pag 1-pentanol lang, actually, some others wouldn't even indicate it. But the OH is located in other than terminal carbon, then you have to indicate it. Okay, so enough for the naming. I think you are already refreshed with naming our alcohols. Na you just always have to identify your straight carbon chain that contains your OH. In this case, for instance, you have 1, 2, 3, 4, 5. It should have been also pentanol, 2-pentanol, but there is a double bond here. So your double bond should have been indicated. So instead of pentanol, no, you have to indicate this double bond here. So you have your pentanol. Okay, but you have to indicate where is the ene and where is the OH. So how do you say that one? You always have to indicate your 2-ol, pentene 2-ol, and you have your carbon 1, 2, 3, 4. The parent chain is the alcohol, not the alkene, no? Because there is a greater priority for those compounds containing oxygen rather than the hydrocarbon. That's why in our name we end with ol. So you have your pentene 2-ol to indicate there 2, and 4 to indicate it is on tene in here is on carbon 4. So you have your pentanol, but all has to be indicated as a CO. Like kung may naka-pentanol, we assume that the OH is in carbon 1, but it's not. It's carbon 2. So pentene 2O, in to indicate it's a double bond, and the double bond is in carbon. So the name is for pentanol. For ethers, simple ethers are frequently given common functional class names. So for example, there's a list for that. There's a lot of common names for our ethers. You have your ethyl methyl ether. So how do you say this? You just have to identify on the alkyl groups attached to your oxygen. So there are 2 alkyl groups attached to oxygen. Oxygen is bonded to carbon-carbon. So just have to identify this one. So you have your ethyl here and your methyl. And usually you have to say it in alphabetical order. Okay, so alkyl, methyl ether, you have diethyl ether. You have here your phenyl and you have your third butyl. So mag-una si butyl kaysa kang phenyl. So you have your third butyl phenyl ether. Or you can also use the substitutive names. When you say substitutive names, we have to consider this one like our main parent chain is our alkene, no? And then this one becomes our substituent. Monomial substitutive name. So the OR here, the O, the one with the fewer carbon attached to your oxygen becomes the alkoxy group. So here this is a methoxypentane, but we have to indicate where is the methoxy, and this is on carbon 2. So you name this one as methoxypentane. Alternatively, you can name this one like in this manner. So you can have your methyl, and you have your 1, 2, 3, 4, 5 pentyl, but pentyl is not, the O is not bonded to carbon 1. So you don't say pentyl methyl or methyl pentyl ether. You have to indicate 2, 1, 2, 3, 4, 5, 2 pentyl methyl Alvin OP. So maguna si methyl. Methyl 2 pentyl ether. Okay, but I can also say in substitutive manner like this one. Okay, so much for this. Already know how to name. Just have to review on your organic chemistry 130 nomenclature. And we also have another kind of ether, which is cyclic. We have the oxacyclopropane here, like this one. So you have your 1, 2, 3 membered ring. So you have your propane. Okay, you have your propane. And you have your cyclopropane, but you have your oxygen here, so your oxacyclopropane. The common name is oxirane. Or you can have your ethylene, you have your oxide. The common name. You have also the oxacyclobutane. So you have the butane, oxacyclo, which means there is an oxygen in the cyclo of butane. So one oxygen in the cyclic ring of your butane. So oxacyclopropane, oxacyclobutane, 1, 2, 3, 4, 5, but there is an oxa in the cyclo, so oxacyclopentane. There is 1, 2, 3, 4, 5, 6 cyclohexane, but oxacyclohexane because there is an oxygen in the ring in the cyclohexane. There is an oxygen, but there are 2, so you have dioxacyclohexane, and you have to indicate where is it located. So have 1, 4 dioxacyclohexane. Okay, and here you have your polyethylene oxide. You have your 1, 2 ethylene, polyethylene, and but there's an oxygen here. You can also call this one as an oxide. So like this one, you have your ethylene oxide, ethylene, and you have your oxide here. So again, so for this chapter, we will be focused on the properties and reactions of our alcohols and ethers. And later we'll see on the reactions of our alcohols, no? And alcohols, whether it's primary, secondary, or tertiary, will affect on its chemical reactivity. So at this point, we should be able to know on the degree of the alcohol, whether it's primary, secondary, or tertiary. So here the structure here is the albuterol. It's an asthma medication, and also have the vanillin here. Our task is to name the functional groups present sequences. Balik-balik mo na. I think you already know this one. So, you know, name the functional groups and classify its 1 degree or 2 degrees. So, I already know there's an alcohol, there's an alcohol here, OH. I think that from the structure itself can already classify. So, what about albuterol? What is the degree of our alcohol here? Anyone? Okay, Camille, unsa na siya mga Camille? Albuterol, so 1 degree, 2 degree, or a 3 degree alcohol? Camille? Anyone? There are 2 alcohols you can find, right? So albuterol you can have here, it is a 1 degree, and this one is a 2 degree, and here you have a phenol. Here you have a phenol, walay 1 degree. Here. But you're asked with, that's why you ask functional groups, right? So you have here the functional groups. You have your amine. You have here you have your aldehyde. Here you have your phenol here, and you have your ether here. O carbon and another carbon. I don't know why you still ask for the functional groups, but at this point, dapat master naman functional groups now. So I'm only interested on the degree of the alcohol here. It's 1 degree. Whether it's 1 degree, 2 degree, or 3 degree, because it will matter later when we'll be talking about the reactions. Okay, so let's talk about the properties, the physical properties of alcohols and ethers. So its physical properties can simply be derived, of course, from its structures. So here we have ethers. Those are all alcohols. These are ethers. Okay, generally what you can see in the table later, you know that ethers have boiling points that are roughly comparable to that of hydrocarbons, having the same molecular weight, but that alcohols have much higher boiling points comparable than the comparable ethers or hydrocarbons. So for example, if you have your diethyl ether, no, it's not a diethyl ether, you have your CH3, CH2O, CH2, CH3, having a molecular weight of 74, the boiling point of diethyl ether is 34.6. And if you try to compare that with pentane, having a close molecular weight 72, the boiling point is 36. So this is what is being said here, that ethers have comparable boiling points to that of our alkane. But when we try to compare ethers to alcohols, what you will see is that our alcohols would have a higher boiling point than our ethers. So for instance, we try to compare diethyl ether, like having a molecular weight of 74, and we try to compare that with alcohol of a similar molecular weight. So when you try to compare to organic compounds, there should be like the same